welcome everyone to the workshop. And basically, I just give a short intro that we need somehow to arrange our database and to be it shareable between different projects and to make it available. So that's why step by step we come to the idea. So maybe Grasshopper could be a platform for the projects to share the information between and to make some data flow. First of all, I would like to start from some basics of the Grasshopper. The first program actually is Rhino, and basically it's, as you can see from the screen, it's a simple CAD software that was originally designed for that way, but originally it was planned to be very appropriate for the product design. And it has very nice opportunity to model with different NURB surfaces. And that's why people just get into it and use for many different shapes. So it exports really like a product ready high level surface quality. And that's why this Rhino software was well accepted by different industries and so on and so on. They will be developing. The interface is really nice. And actually, that's the window, how it looks like. So you have different point of view. You have top, front, whatever you want. And in this case, I just want to show that if we take a Rhino itself, like an CAD software, I use it like a one key point to store all the information about the project. So for example, I can show you now some actual projects that we are doing now. And in one part, I have some two-dimensional drawings, some laboratory description, explanation, different mind map to explain and to discuss with our colleagues. So different calculation, but also in the same folder, there is, for example, some 3D geometry that can be used for the experiments and so on. So different 2D, 3D, whatever, some preparation for the 3D printing. So for example, if you do some geometry, you can easily export it because you have in Rhino actually quite nice opportunity to export different geometries with quite wide range of formats. So maybe it's not the biggest one, but I expect that probably Rhino gives the widest possibility of the formats to export and to import. So if we go to some geometries like from the first phase of CO1 projects, you can see that all our shapes up to the last XPS block. So everything was modeled and keep in. So you can see the reinforcement, the textile reinforcement, XPS, also the shapes that I expected, different cross-section that were used for the visualization with 2D. So from my point of view, it's really convenient that we keep everything in one file. So, and of course, not only some drawing, some CAD, but as we do some 3D scanning, also this model can be easily inside the Rhino window. So it's not a big problem to load them, to discuss them. And then, for example, after the test, the scan geometry is done. So we can compare with the original one, make some processing, some scaling, so whatever you want. And as you can see, everything in one window. That's one of the key things that I really like from that. So you do not need to switch between different 3D modeling, CAD and whatever. So after I switch to Rhino, there is no need for AutoCAD or something like that. So I find it more convenient for 2D drawing as well. Yeah, that's what we say about the Rhino itself. But if we go 1 second, for example, yeah, that's the Rhino. And actually, if we go on top, you can see quite wide range of different tools for surfaces, solid, curve, whatever. So for different transformation, mesh tools are really nice. Yeah, but so far it's only Rhino, a CAD software. But then somebody decided to do a really good programming tool for it. And that's exactly Grasshopper. So originally it was done by Side organization. And the Grasshopper you can launch from the Rhino itself. So it's like a simple plugin. So, and let's say not many, but some years ago, there were two separate programs. So first you need to load and buy the one, then you should take the second one. But now they merge together, so it's much easier for people to play with this set of softwares. And then you just actually press it, so you have another window. And that's like a normal classical, let's say, working set, that you have a window of Rhino and you have a Grasshopper as well. So the key thing here that they are interconnected. So Grasshopper actually is some kind of virtual representation of what is in Rhino, because here in Grasshopper everything is parametric, and I mean everything is programming. In Rhino it's more like hand drawing, hand modeling. So, and let's say we have some just a few words about the Grasshopper interface. So it's a huge canvas that probably I never reached the end, but most likely it's infinite. But actually, yeah, you have a huge canvas where you can write your code, and write the code means that you have different functions. Then they are categorized. They have some primitives, then mathematics. So I think to get into all of these groups, it's a long story, and we will not touch it right now really into deep. But of course, with different YouTube videos and whatever you want, you can play with all these groups and different tools. But just to give some short intro, that if you have some function, for example, we have a number slider, so that you just drop in and you can use it easily. So, but then you, for example, take another input, a simple panel that represent the values. So, and that's the way how you construct your code. So you're not really typing in, but you're constructing it. So you're developing this stream of the analysis of the codes. So then if you change the parameters, you see them afterwards. So then, for example, you do some summation, you copy this block, and then you have the function works in this way. So from the left to the right, and then it's just increasing, and so until you reach an absolutely huge code on whatever you want. Yeah, that's, let's say, only the numbers, but for example, you want to interact with real geometry, and then you also can, for example, grab some of the instances. So now you see that before we had just simple gray geometry, so it was hard drawing inside Rhino, but then we just copy it, and now we see the same instance, the copy of this geometry inside the Grasshopper. And now it's stored inside this container. So then we can take a look what is inside. So it's the representation of this geometry. And then once it's in Grasshopper, so you grab it somehow, you can then manipulate it, modify it, whatever you want. So, and I think this is quite simple example, but now maybe to give a bit more intro, I can show you some modeling. That's actually what our main topic today, but we will go step by step. So not to make any confusion, I hope so. Yeah, and then as you can see, what I told you, that the canvas is unlimited. So basically you can assemble one by one the huge code, whatever you want. And now we just go to another representation of the model. So here in the Grasshopper canvas, there is some geometry modeled. That's exactly how the code looks like. So there is nothing about some Python programming. There's only this visual programming using the wires. And if you right-click each of the module, you can see the preview. So if they are gray, then basically you do not see what is inside. But if you set the preview, so for example, this code is modeling this type of TRC chair, for example. So you can take a look that the code starts from some input parameters, and then we go through the line and we finish with the final geometry, with the surface. So that's actually how it works. And but in this case, none of the geometry from Rhino was grabbed. We started originally in Grasshopper. So we model some points, some key points that controlling, and then we can control the X, Y, Z of these points. So if I click it, so you see that I select the representation of these points. And then, for example, if you change some parameter, you have the deformation of the chair. So, I mean, with these 5 points, they are collected in this unit. Everything can be, I mean, you model the key parameters and then you have the points. Then you use points to construct a spline that giving you some shape. What is that? Something also interesting. But then we need to expand it because the chair has some special shape. So then we take the same points, we apply, for example, the deformation function to move them. Here we construct the vector. What's the logic behind how we can move each point? So basically this small code on the bottom really give you the vectors for each point to move it. And then after the movement, we have another curve that also we move to the sides. And by this, we create a load geometry. So as you can see that we start from very single points, we duplicate that, we modify them somehow in this space. And by this simple code, we assemble a chair that is parametric. The key thing of the Grasshopper, why it's so nice, that basically you see the whole code from the very beginning to the end. And actually, you can simply grab, for example, part that is developing the vectors and modify it according to your wishes. So maybe you need some another logic, you just replace it, but the other parts of the code remain the same. So then you have this geometry on the right, and they are really like a virtual representation, so they are not real. That's why some of the models, they have under the right click, the very important button, bake. So if you bake it, you transform the geometry from the virtual reality of the grasshopper to the reality of the rhino. So now it's like a solid object, let's say, not the solid. Yeah, it's better to say that it's a shell. It's not the solid object, but anyway, it has some really representation in Rhino. So then with different tools that you can see inside the Rhino, you can modify it, whatever. So for example, you also can export. And then if you select the file, the format you need, you can export it according to your requirements, for example. So then you can modify it, and let's say, because if we bake it, it's like it's going to be solid already in Rhino. But then we just switch on and you see that I changed the parameter. So there is another instance of this chair. So we also can. So there will be another chair. Yeah. And with this simple modification, you can create a different set of geometries. Yeah. Each model has the input and the output. That's actually how the function works. And you can see the description that moves. You need to give a geometry. You need to give a translation vector, and each of them has like the mirror, geometry, and the plane to do so. That's the normal procedure. Sometimes, for example, if you have the input, you can also give your expression. Let's say we multiply it by 2. So it means that this number is already changed. And then you can see that now we have completely different large chair because we multiply them by 2. Yeah, as you can see that the canvas is unlimited and you may have really big representations of the code. And there is very nice option that, for example, you have a part that it works fine and you just need to minimize it. So then you can create a cluster. So it's really drop inside, and with double click, you go. And so you go to the isolated part of the code. Then, for example, in your main code, you select that this is the vectors, this is the loft, and so on and so on. So this is the input parameters. So in fact, you have the input parameters block, you have the vector analysis, and then the loft. So now the code is much smaller, but if you have the problem with one of them, it will be in red color, so you know exactly where the problem happened and where you have to go to fix it. So that's why, as I explained, the good thing from Rhino that you can split, you can, let's say, add new features. You have the input, you have the output, you have this chain, the workflow. And if you see something is missing or you need another fixation of your code, you need to replace it, you just go inside this part and you edit, you modify it. So that's like a short discussion about the main functionalities, and you see how the simple geometry is created. Now the chair somehow deformed. Okay. Yeah, and just to switch off the code, there is another point that you disable it. So you see that this code is now completely off. The information is not passing this codes. That's why the next one say that we have a problem, we have a mistake. They are failed. So that's why if you see the red one, that's something not working. Sometimes they are yellow like this. That is not actually the failure, it's the lack of some information. But it's still sometimes, for example, you have a large set. Some of them can be yellow because you have some specific exception, because let's say 90% of geometries or points works fine, but 10% are out of the scope. But still, the code is functioning good. So that was, I think, the very short, brief intro for those who just started into the Grasshopper and Rhino. Forgot to say that instead of the functions that already in the group, there are also some of them for scripting, and they also have one for Python, and you just drop it down. And for example, if you click it, you see the possibility to give your own code inside, and then you can easily give some different inputs and outputs, write whatever you want. And that could be, let's say, another degree of freedom if you want to type your special code inside. But it has some limitations, especially about the libraries. It's not working very good. The Rhino 7, the 8 one is much better in this field. But anyway, all these questions can be managed even with the 7 Rhino, so I will show you later. Okay, then let's go to the actually workflow. I developed kind of the first outline, the sketch, how the workflow that join all the projects can look like. And first of all, for example, if we go to the groups, we can provide our own components that you can see the group SFB. It's only for the explanation, so that we have a different possibility to post our own components. So if we agreed, then we publish them so anyone can download it and easily share it. It's not really a server. I put it locally to test. But for example, you can see that we may have a database of the geometry, different CT scans, material database, and the database for the production. So, and let's go to the geometry. And for example, the first is really initiation of the geometry. So how we can start. Let's say here, it's our module, how we load the geometry from the database. So you just put it here, and then you give different tags. It can be from different projects. You are absolutely free. And then, for example, you drop a list. And here, automatically, you have, according to your text, according to your selection, you have a different list of geometries. And then you just make it visible. So then this information is stored here, for example, in the database. And for now, for the research stage, all the database is shared using JSON files, but of course later we can switch it to another type of database structure. This format gives really nice interaction, and you can adjust it manually or according to your some software. So, but it's quite open. I just open it. If we go inside, that's you can see that this file store some system information, different IDs, that we really share the data correctly, that we do not have any duplicates, so we can discuss different schemes. We see some metadata about the author, how it was created, who did it, some description, and also you have a list of parameters The geometry itself is given here in way of expressions. So you just try somehow. I mean, it's according to your software that you use normally, according to your conventional software. You just develop the code, you try. If it works, you fill the vertices with your expressions. Then you have the lines and basically the faces. So the structure is pretty simple. And the thing that here in the expressions, you can see that the mode is expressions. You can use any of expression that match the Python mathematical library. So that should be quite wide possibilities. And actually Grasshopper reads everything, and then we just drop here another panel so that we see the available parameters here. So what we need. And the default parameters is here, but you have two input parameters, as you can see, x1 and x2, and we just put the slider and drop it here. So then this slider is going to be changed, and then you see the deformation of the geometry. So now the code loaded on the JSON representation with your expression, and then using your explanation, how you describe the position of the vertices and the lines. So then you can easily modify it. That's exactly how you code it. You give the list of parameters that is assumed inside the code. And now you see that that was x1 and then there's x2. So if you delete one, it go back to the default one according to your representation. Question how we can export it. For example, in Grasshopper, you play, you construct the chain, then you see that the logic works, then you post it into the JSON according to these expressions, and then it works like this. So we publish into the database your code, and then everyone can just download it, this module, and play with these parameters that you predefine. And then as export, for example, you have these surfaces. I just reduce it, and then you set one parameter, that's like one module. And then you change somehow, so you can easily publish them to your solid representation of the Rhino, and then you can export them, you can calculate, so in any possible combinations. It's up to you, and you see they are different instances, but from the same code. It's not the only functionality, because there are different types of geometry you can store, and the way how they are shared. The same model works good with the 3D scan. So actually, if you do some 3D scan, you also publish in the same way. And this 3D scan is another JSON that express and explain how it works, but actually the cloud of points stored separately. So you can use it like in common format, but then Grasshopper actually reads everything and give you here. Of course, it's not anymore a surface. You see there's nothing is here, but it's given like a mesh here with another output. The module itself is just Python code that was developed using the same module that I showed you before with an empty one. So another option that you have actually different other possibilities. I mean, this is exactly the same, and there's something for arch. For example, that could be a simple rectangular beam. Then you extrude it, or it can be a sandwich. And then, for example, if you select them, so the arch is given with some parameters, so you have a shell to make some analysis, some calculation. Then these objects are actually all the same. I mean, you have the list of parameters, but they are all based on the same principle behind. So some of them are without parameters. We can publish also some instances that are fixed. I don't know, for some reason, maybe you have some special request. So then we can publish it in this way. The I-beam, some another sample, and for example, the water bomb cell. So it takes time because now the code differently works. Actually, that was, I can go inside and we have another JSON representation, but here we have that geometry is given not by the expression because parameters are listed here, as you can see, A, B, C, and gamma, but the code actually running in the external Python code. So that's why here we can develop this kind of a template. Your geometry is just given like the code using different libraries you want. So you can see that the kinematics of water bomb is imported from the Python library. So then the proper object is used. Then we have a list of parameters for this type of geometry, and we have output of vertices. All these helpers will be reduced later, but if you are like a user, you can just need to type in your logic, your code inside very small set of this code. Then you just publish it, and you see that before, we go to the default version. I want to show you another thing, that sometimes the Python coded library can be quite heavy and it takes time for them to run. So that's why the code works like creating external instance of the Python that is running constantly on the background. And for the codes that are created from the JSON expression, they are quite lightweight. So you can see the response is really small. So it's just milliseconds. Of course, this milliseconds can be even less if you do not have this canvas. The smallest canvas, the faster processing. If we go to the water bomb, the initial load may take a couple of seconds because it loads the library, but then afterwards, any modification is just also some milliseconds. And then we can see, for example, the first parameter, we can edit the slider. So, and then we put the minimum to 1000. I just want to say the numbers I select without any special purpose. And then if you just move the sliders, you see the response is quite fast. So you can easily play with the water bomb geometry. So basically, this module covers, as far as I see, more or less all the possible formats that we use, and you have different options to code it. Either it's a 3D scan, or it's a fixed, or it's expression-based, or it's a completely Python where you have no limits of any possible libraries you want. For example, for the water bomb, you give also the limits. The program said that what is the minimum and the maximum. If you accidentally put something out of this scope, then the program will use either maximum or the minimum. And exactly these parameters are listed inside the Grasshopper. The purpose to give you a vision of possible options is not about everything is just expression, it's only equations, but the way how is more comfortable for you, because the workflow here is intended not to replace your conventional workflow, but just to give a connection between the projects. So if you, for example, for the long term developing everything in Python, then you can just use your previously developed, you create the gate according to the template, and you just run it in couple of, I don't know, maybe 1 hour or something. You need to attach your new geometry to it. That was the initiation of the geometry, but then we have to construct our assembly, and some blocks are still in the process of development, especially when you have a cell input and you need to give a tessellation. In the field of the tessellation, there is another two options. Once you have a cell like already deformed, and you apply some logic and you create the whole slab or whatever, or your geometry is started from this point. So you do not develop like a single cell, but your single cell is inside the code. So basically it's another representation of the code, but here another objects from the library used to create the full tessellation. So you have different parameters, and you see here that now you have also 4 of them, but also in different directions, the number of the cells. So that's why it's exactly the same library, exactly the same principle that was used for the single cell, but now for the tessellation. So, and then we can now, for example, bake it. So you see now the physical representation of this water bomb. And if we go to the database, of course, it's a matter of discussion. We keep it in this parts, or we, for example, the initial geometry for the single cell, then the tessellation, we can make a different codes. It's up to us, but for now, it's like subdivided that initial cell, initial representation unit is like one part of the storage, and how we manipulate, how we create the large structure, then let's say the superstructure is different part of the library. But actually, the logic is behind absolutely the same. The parameters, it's only the matter what you create at the end. As you can see in this canvas that is subdivided into different groups, and they are all with the titles. So each of them, depending on what's the functionality. So we start from the geometry. It can be anything you want. And then you go to the assembly, to the LCA, different materials. Then also the model assembly, structural analysis with different softwares, processing, automation, optimization, production. So then now the explanation will be based on one of their water bomb cells. In this field, we assemble it. For now, this block is still not very active. That's why just passing the geometry here. And we have the geometry, what we assembled before in this point. But then once we have a geometry, we need to construct other components for our objects. For example, we need to create a solid body. So then there is another unit that you can see that creating a thickness. Each of this module is some code behind the cluster, what we already discussed, or it can be different the Python code, a separate one. Anyway, now in this phase of the workflow, we are going from an abstract representation of the geometry to the physical one. So we give all the parameters like the mass, volume, area, whatever. So now we have some physical things to express it. So there is another module here that we reach a database for the materials. And also it works more or less in the same principle, so that we have some element. For now, it's only one material for test, but you give your tags depending on what you want, the region, you select materials, what we published before, for example, and then it gives like an object all the information to the solid. So here under this module, we have geometry plus material. We have calculation. We know what is the object, what is the volume, what's the other physical parameters, and we know what is made for. Let's go now to the database of the materials. And then we have this concrete. In this workflow, one of the ideas that we have Grasshopper and Rhino to be used like one source of our interaction. So to make our database not like a solid storage where you need to find through all the folders or something like that, but it should be really like a design-driven solution. That's why if you are a user of this workflow, you download, for example, the material, you select this material, you can calculate already with that, because this database contains LCA data. They also contain the experiments that you want to attach, different material models. And that's why if you wire this to the solid shell and then assemble the whole geometry, you can then easily wire it and extract different data for the VM analysis. And that's in the process of development, the gate for different other software solutions. So it means that this material database contains everything you need to express and to summarize all your research regarding this material. That's why if we go, for example, to this material, you see again the initial JSON file that explains some technical explanation. It goes some very basic mechanical features, but they are more like for common use. And then later you have the explanation of the components, the recipe, some other mixing, some other related functionality. You can give the notes, but also the file contains the catalog of the important data, files, pictures, web links, whatever you need. For those who are not, let's say, from your project, people not willing to dig through all the billions of our folders. But if you use this material, you can just, for example, click another button and you have another browser of all the related materials. So for example, you have this basic representation, you have the website of who is producing it, and then different other PDFs, for example, with the materials and so on and so on. So in fact, if it's not your project, but you have an easy access, one point of access for all the information related to this data input. So of course, it should be developed quite properly, then you have a nice database. So also you have a link to the publications related, because I think in the research field is one of the key things that you really list some publications that is somehow related, so you can find the recent information about this material and where it was used. Getting back to the database, as a separate file is another LCA that was loaded from the APD, and you see some basic information, all the modules that is absolutely known for us, but actually you give all the LCA data inside. So then the documents, they are stored in the different locations. So for example, all the publications, citations are also listed. In fact, the Grasshopper here designed that you do not need to store all your PDFs or some information in one location. You just give the link that, look, in the server, I have some PDFs in this area, some Excel sheet in this one, and then you summarize everything into the catalog. The one who is you sharing this information can access through the single button. So, but no need to duplicate the information. You can keep it in your own project folder, for example. Exactly the same story, but we just type different tags. So this is a Solidian grid. Here, the same unit that developing not the solid shell, but developing simple textile mats, 2 layers, but yeah, they are still under developing. So then, for example, you have a solid concrete element, then you have a textile reinforcement, and maybe you have some XPS blocks. So basically all of them can be just put into one assembly. So this is one of the most important model assembly blocks that put all the information together. And this is one of the main source of your virtual model. After this model, you can do the FEM analysis, you can do the LCA processing and whatever you want. But first you have to assemble the model that represent your reality. It should be another helper that just extract different data, or you can extract some FEM analysis gate and then run here a pipeline in using, for example, ANSYS, RFM, Abacus, whatever you want, and then visualize the results. After this model, we have some representation of our reality. It's an abstract model. It's not detailed. It's not dive deep into the every single connection, bolt, whatever, but that's exactly where Carlos will introduce it. So how based on CO4 project, how a detailed modeling can be done inside Grasshopper, because this workflow, it's really like a global scale. We communicate inside this workflow, but everyone is, of course, able individually develop very precise modeling inside your own project. So that's why please consider this like a real communication tool, but not the up to the very single bolt. All this workflow and the tools is available for any project, but it really depends on what you're doing. If your project that generating geometry, you of course your task and your main tool will be this element. This element can be if you want to share this geometry. Of course, you use your own conventional software, you're doing the research in the conventional way, but if you're willing to publish it and if you want to share with other projects, you just put it there. So now somebody sitting in Aachen developing a geometry and then publishing. Instantly, if I'm at the same time in real time in Grasshopper, I can just put recompute and then I see this geometry here in my drop list. So I put it here and then I can use it immediately. Then, for example, I give like input this information, but then I want to cast the concrete. I want to do some experiment in the lab. So my main task is to develop actually the model, the idea behind the geometry, material, and other production units. They should have something like a sandbox where users can easily assemble the model. And this publication unit, let's say, will be able to check if you're missing some important information or not. So we finish with the model assembly. Maybe here I will stop briefly for the so-called instance, because actually the material model, geometry and everything is some kind of it's a model. It's not a real representation of the object. So if you, for example, you never have the same beams, you never have the same concrete mixture, there could be different. So that's why another idea that for each, let's say the model, material, solid shell, whatever, we can make some kind of offspring, like an instance of this object where you put calibrate really tiny calibration of your experimental data. And for example, in the model assembly, let's say you develop some model and for example, you have this point here, even better to show it like with this, that you have the virtual representation of this model in this instance. But then you cast, for example, 2 beams, or you cast 3 of them, each of them can be somehow different. That's why on the left, you have some tiny calibration possibility to adjust it and record in this instance exactly your experiment. And that's why you can put, for example, experimental data deformation and all your Excel from the first shell, from the second, from the third one. They can be saved on your project folder. No need to share it into the database, but then projects can also exchange these instances between each other, not related to the model, but really special representation that comes from reality, let's say. And of course, you can also take this instance and download it and use the data from this specific instance for some further processing. Once we have the model, then we need to enrich it with some production data. And that's why we go to the geometry tessellation and the production model. It's actually the same story as you can see from the database. For example, we may have a representation of different production techniques we use: 3D printing, extrusion, casting in different location. So we are not limited to the number of these inputs. In the same way, we keep the data in the JSON about the production, also some systems, some metadata, and also, as you can see, compatible material, because you have one concrete for the 3D printing, you have a different concrete for another type of production. So you give exactly compatibility that users that are using without you are not making any mistakes. Then, of course, one of the key thing is different production restraints. So that's why we specify, for example, if we use extrusion, this is our nozzle limit. If we use 3D printing, this is our limit. If we have extrusion, you extrude one stripe, but then you are limited to bend it because you may have the cracks and the element can be not good for you. That's why in this file, in the database, we also specify what could be some limitation of your production. You give some notes, also the catalog of the related information. So that's why if we go back to that, we have exactly the same browser with the files, with different PDFs, whatever you want, publications, and also you can keep some, for example, media files, some photos, videos, if you have something from production that as you think is better to represent the production features. And of course, each production can be also provided with another LCA data that giving some maybe processing codes. Basically, you have all these features, all the groups in the same way like for the materials. You just specify especially to your phase that you need. So then after the production, so let's make another example that we produce the shell. We have a concrete, we have a textile, we use it from the model assembly, but we may have another components to produce this element. So for example, formwork, some another special components. That's why can be some spacers, for example, some another features that are not mentioned that is not needed in your main model, because for the structural analysis, you do not need all these special components, but they affect the production, they affect the LCA output. That's why you also model it. But you can see there is another group with the component, production, project site, and you can exactly model your workflow in the different manner. So you are modeling here all your life cycle of your project. This is the final production, but then you have the components. You just drop them inside here. Another point, just briefly stop. So after the production, actually answering the question how that could be related to the other projects. This could be the model, for example, for the projects that doing 3D printing, textile laying, extrusion, so on. So from me, I do the model, I check it, I prepare some numerical analysis, I develop it. Then this line passes to another project that taking this production, selecting what they can produce, what's the actual production, and they, for example, can check with another model for the limits of their production. Let's say I develop the model in such a way that somehow I am crossing the limit of the inclination of the shell or whatever. So this model will show that, okay, that's fine, but with this production, please do not cross this limit. And then after the projects who are developing different production systems, they can use the data out, this model, for their gates to develop control of the robot, for the casting, for the 3D printing, for many different CNC procedures. So basically this model providing the information for the slicers, for the 3D printing, for any other control. That's why you do not need to extract data separately. You just pass this data out, and then we can develop this module together, that afterwards you just export it and you have a G code for your system to run and to produce it. But it's more about the production. So we just go a bit to the bottom because we have the model and we need to deliver it to the site. Let's imagine some virtual site that we bring it also to the site. Maybe we need some another production or some another components. So actually you also here modeling different components that you need for your final structure, some supporting elements, some, I don't know, windows, any other thing. In fact, what you can see under the LCA, you're modeling all your life cycle that comes after the site to the LCA module. And here you have the assembly of the whole LCA project and everything. Afterwards, you see it in orange because it's not yet developed, but this is the stages after B1 until D for up to demolishing, recycling, and up to the end. So if you're modeling here the whole life cycle, you have actually in this, I think, quite nice grasshopper representation, your life of the object. But the thing that you need somehow to see the results. So that's why the LCA, because all the data are stored inside, especially for that. And then I have another button that starts another graphical interface. So that gives you the overview of your actual stand of the project. It has, for example, the list of your data, and you can see different designs. So you change the parameters, whatever, and this window is a real representation of your model in Grasshopper. For example, you play with different parameters, and that's why you see energy and all the indicators listed depending on your design. For example, here you can see this parabola that I was playing. That's the non-linear change of the water bomb thickness. So it's giving more and more if I start from, let's say, 9 millimeters, as far as I remember, till 100 millimeters. So you can see also the same statistics for all the different phases of the LCA. And then for example, then you switch between your projects. So you see the difference, you have some statistics. And the good thing here that you modify different parameters in Grasshopper, instantly you see it, so you can calibrate it. You select the most appropriate one, and then for further study or some processing, we can add different pages also to this graphical interface, or you can export any other formats. So maybe for your publications, whatever you want. So that's why this window is a real representation of what's coming to the LCA model here. That's why we now are from the left, from the very geometry, from the very first point of geometry. Then we pass through all these modules through the production assembly of all the LCA chain. We are able to visualize the data. We see the statistics. We see how it changes. If you change some parameter, you can drop different materials. And for example, getting back to the possible scenarios, now we use one concrete. But let's say another project develop a new mixture, you just wire it or you select the drop-down list and you have instantly the feedback of how it influences of all the LCA indicators immediately. And then you can go back or during the online meeting and say that, look, that's very nice, but in these parameters we have something. And of course, with some very brief numerical simulation, you can see that mixture is very nice. It gives very nice reduction of the footprint, but unfortunately we are not passed for some production limits or we are not passed for the structural limitation that is here. That's why the workflow is able to give you in real time the feedback about all these parameters and you can make your decision. That's it from the workflow because basically that was the last thing. There is nothing more left.